Hello, welcome to our third instalment on transition metals. Today we're going to have a look at how we draw complexes with multidentate ligands and also how these can lead to the formation of optical isomers and how to draw those. Just as a reminder of our two bidentate ligands that we need to know about are 1,2-diaminoethane and ethane diorate. If I was going to draw these as a structure, I would draw this. I've got two lone pairs here on the nitrogens which can form two dative covalent bonds to a complex ion, meaning that this is a bidentate ligand. It can form two dative covalent bonds, and then ethane diorate would be this structure. So let's have a look at how we draw our first example complex. So we have a copper ion here, and we have three 1,2-diaminoethane ligands. So this is the formula for 1,2-diaminoethane. There are three of them. There is a 2+ charge on the complex. This is a neutral ligand, which means the charge must be due to the 2+ on the copper ion. So when we draw these, we start by putting the copper ion or the transition metal ion in the middle. And then the easiest way is just to draw in an octahedral geometry the 6 atoms that are going to provide the dative covalent bonds, like this. And then we just go in and add the rest of the structure. So here's my 1, 2, 3 1,2-diaminoethane ligands. If we have a look at our example complex number 2, the first thing we need to do is work out the charge on the chromium ion. Ammonia here is a neutral ligand, so that won't contribute, but then we've got the ethane diorate ligand. We've got two ethane diorate ligands, which gives us a total charge of 4-. The complex has a charge of 1- overall, which means the chromium must be a 3+ ion to balance that up. So I'm going to do the same thing as last time. We're going to put a chromium 3+ ion in the middle, and then I'm going to draw in an octahedral geometry, first of all, the 4 oxygen atoms that are going to provide the dative covalent bond from the from the ethane diorate ligand, and then I'll fill this in. Sorry, apologies, mistake there, that should be a single bond. And then I need to add the 2 ammonia ligands, like that. Okay, so let's have a look at our third example. In our third example, you can see that we're going to be dealing with an unfamiliar ligand. The 1,2-diaminoethane and ethane diorate you have to know the structure of, so those two I introduced at the beginning. However, you could be asked to apply your understanding with an unfamiliar example. So let's put our complex ion, our transition metal ion at the middle first of all. It's a 2+ charge because all of these ligands are neutral. So the ligand we're going to be dealing with is 1-phenanthrene ligand, which is abbreviated as PHEN or Phen, and I'm going to call it Phen from now on. So we have 1 Phen ligand and 4 ammonia ligands. The Phen ligands bond by nitrogen atoms, as do the ammonia ligands. So I'm going to draw, first of all, just to try and keep this nice and simple, 6 nitrogen atoms and their dative covalent bonds. Like that. Now I'm going to tackle dealing the phenanthrene or Phen ligand around here. So this is a little bit on the tricky side, so I'm just going to look at this structure and go, right, I need to turn it on its side. If you wanted to, you could actually draw it out on its side to make it a little bit easier. But looking at the structure, so I've just drawn this part of the structure now. And then in the middle there's a 6-membered ring, so I'm going to draw a 6-membered ring in the middle. So I've drawn that bit there, and don't forget to add the double bond there. And then these ones are also part of 6-membered rings. So I draw that like that. See, it ends up being not the easiest thing and not necessarily the perfect diagram, but that would be acceptable for us. So I've drawn these parts now, and then I'm going to add in any double bonds. So I'm going to need a double bond here, a double bond here, and a double bond here, and I'm going to need one here, here, and here. And then all I need to do is go and add the remaining hydrogens for my ammonia ligands. Okay, so we've dealt with how to draw complexes. Let's have a look at optical isomerism. Now, an optical isomer is when we form a non-superimposable mirror image. You'll come across this a lot more when you study organic chemistry. I'm just going to show you simply ones for transition metal chemistry for now. So we've encountered this complex before. So remember, nitrogen, 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 lane pair, H2, 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 like that, and then add in my dative covalent bonds. Okay. Now there will exist a mirror image form of this, and the easiest way to do it is start exactly as we did last time. Like that. And then I just want to draw the mirror image. So in this link between the diaminoethane molecule was over here in this molecule, so its mirror image is going to be here, and then here, and then here, like that. So let's have a look at an example with the ethane diurate ligand. So again, with this one I'm going to have to work out the charge on the transition metal ion here, because we have a negatively charged ligand. So we've got two ethane diurate ligands, which gives us 4 minus charges. The water is neutral. That complex has a charge of 2 minus overall, which means the copper must be a 2 plus ion. So let's draw our octahedrally arranged atoms that are forming the dative covalent bonds here, like that. And then we need to add the parts of the bidentate ligand, and then obviously this is H2O OH2. So if we were going to draw the mirror image form of this, we'd start exactly as we did last time. So this ligand, this bidentate ligand here is going to be flipped from this position to this position, and I realise the way I've drawn it I haven't left myself enough space. And then this ligand is going to be flipped to this side. Like that. And then H2O, H2O here, and then H2O here, like that. So, just to summarise, that optical isomers can exist in transition metal complexes where we have the mirror images, the non-superimposable mirror images of our complexes. It's worth us just thinking about the last multidentate ligand that we need to know about, and that is EDTA. EDTA is an abbreviation for ethylene diamine tetraacetic acid. You do not need to know that, but that's where the abbreviation comes from. You do not need to know any of these structures. This is the skeletal diagram of it. The reason it's called ethylene diamine tetraacetic acid is the ethylene diamine is the non-UPAC name, so the trivial name for this group here, and then this group here, which we'd call an ethanoic acid group, its non-UPAC trivial name is acetic acid. So we've got ethylene diamine 1, 2, 3, 4 tetraacetic acid, and this is it with hydrogens attached, and this is the ionized form. So we would call EDTA has a charge of 4-, and that's something we need to know. And it forms 6 dative covalent bonds. If you have a look here, this is where the ligand has complexed. So there's a dative covalent bond there, one there, one there, one there, one there, and one there. You do not need to know, be able to draw the structure, but you do need to know that it forms 4 coordinate or 4 dative covalent bonds. Sorry, 6 coordinate or dative covalent bonds. Thank you very much.